So hi Sushan and welcome to our final day. And we'll now have the second talk by Sushan. She's given one on this thing. We'll put on chat. Okay. Yeah, so Sushan, we can start with you. One sec, I'll just make you a co-host. One second. Yeah, just a minute. Where is? Okay. Yeah. So Sushan, you're a co-host now, so you can share your thing and
okay.
Control.
Yeah. Thank you, Priya. Good morning, everybody.
Your audio is not audible. I can't hear your audio.
Can you hear me now?
Can the others hear fine?
Yes, ma'am, we can hear. Audio is there.
Can
everybody? Okay, I'm sorry. Yeah.
Yeah. Can everybody hear me?
Yes, ma'am, we can hear you.
Can everybody hear ma'am fine? Please write it in the chat window. Yeah. Okay, there's something with my speaker probably. So can the others hear her properly? Just write in the chat, we can hear. Okay, fine.
Yeah.
So Sushan, you can start. And
it seems they can.
I'll try to see what's our problem here.
Okay. Okay, good morning, everybody. And special thanks for being here on a Sunday morning, which is not easy for everyone. So let us begin the second and the final lecture of this series. So let me share my screen. Okay. Okay. Now, first of all, I would like to apologize to the students if you have posted any questions or comments in the forum. I'm sorry, I did not have the time to go and look at those, but I promise you that I would do so in the next couple of days. And if, whatever is possible, I would reply there. And I am planning to finish this lecture a little earlier than I'm supposed to finish, so that we'll have a little time to discuss questions. So if you have posted some comments or questions on the forum, you can bring those questions here today. So let me remind you about the motto, the main thrust of these two lectures is the history of astrophysics is where we perfected timekeeping. And today we would say more about timekeeping than before. So today what we will talk about mainly is a phenomenon called glitch of radio pulsars. And some of you or many of you may be familiar with the word glitch and also the phenomenon of the glitch. So we will talk about glitch in a little more detail. And please remember that last time we talked about nulling pulsars, which is a phenomenon where all of a sudden the pulses, the radiation pulses that you receive from radio pulsars, they disappear. Now, today we will talk about this phenomenon in which the pulses don't disappear, they're there. What happens is the spin period suddenly changes. So you also know from last time's discussion that the spin period of radio pulsars are changing continuously because they are slowing down. And so therefore there is a continuous change of the spin period. And the radiation is coming out of these objects, and that is coming out at the expense of the rotational energy, and therefore the spin period changes. Now today we will discuss about a phenomenon in which the spin period suddenly increases. Now please try to sort of realize that this is a very unusual phenomenon for an astrophysical object, because from ordinary physics we know that any change of angular momentum, there has to be a torque, an external torque. So therefore, because this is an astrophysical object, there is a neutron star in the sky, and we cannot have external torques on such a system. Now, because of certain dissipative processes, like radiation coming out from the system and so on and so forth, the system can lose angular momentum, and therefore it can slow down. But a sudden spin up means an increase in the angular momentum, and that is something very unusual to experience in an isolated system. Any astrophysical object like a neutron star or our sun is essentially isolated, meaning you are not able to apply an external torque on such a system to increase the total angular momentum. So now, when such a phenomenon is observed in an astrophysical system, something very sort of intriguing is happening inside the system. And today we will try to understand what such a system is, what is the nature of the system which makes it possible to have a sudden increase in the spin period. So let's recap a few concepts that we discussed last time. So the time of arrival, as I talked about last time, this is very important, because unless you have a very precise estimate for the time of arrival, meaning you have a pulse which has arrived now, and you have a precise estimate when the next pulse is going to arrive. So that is your estimated time of arrival. And if the pulse that arrives, the real time of arrival, that deviates from what you were expecting from the system, then you must know why the expected time of arrival is not matching with the real time of arrival. So therefore, you must have a very good calculation for the expected time of arrival. And how do you get this expected time of arrival? By observing the system for a very long time. So you know how the system behaves, and you estimate what is the precise time of arrival, which is averaged over all the properties that you have seen, all the characteristics that you have seen over a long time of observation. And then you have an expected time of arrival. And as I have said, how probably I didn't mention last time, but was discussed in a little bit of detail, if I remember correctly, in the previous set of lectures last year, is that a time of arrival is calculated with a fiducial point on the profile. So you have an average profile, and you sort of mark a point, maybe here, maybe at the peak, somewhere. And then you estimate the delay with respect to a template profile, where PT is the observed profile, TT is your template profile, which you have generated, and NT is the noise, and tau is the time shift, the delay in arrival of a pulse. Now, of course, there are whole ranges of effects because of which a pulse get delayed, or if the spin period of a neutron star is some number of seconds, then you expect the total time difference between two pulses to be that spin period. But it is not exactly so, because we have all these time delay factors folded into your data when it is coming to you through the galaxy. So there are possibilities of various corrections, because all the elements involved in the observation, starting from the neutron star, which is emitting the pulse, then the solar system itself, then the earth around the sun, there are all sorts of movements. So you have to correct for that. You have to correct for various other delays which may happen on the path of the emission being generated at the neutron star and traversing this entire path to the observer. So I urge people to go and look at the book by Lorimer, which I have mentioned in the previous lecture, and understand the details of these delays. We do not really have the time to talk about these delays here, but so there are all these factors, and one has to correctly estimate them, calculate them in order to understand and precisely define the time of arrival for a particular pulsar. Now, once you have done that, and what we have seen last time is one of the behaviors we find is that abrupt cessation of the pulses, the pulse emission, which we call nulling. And these are the characteristics of nulling behavior of the nulling pulsars. So they are associated with drifting of subpulses, association with mode changes, association with switching of emission frequencies, the emission frequency changes. And there is evidence of change in the period derivative, though not in every nulling pulsar. And we have this summary of the population characteristics, which I have talked about last time. And so therefore, so these nulling pulsars are various basically two parameters through which we characterize the nulling pulsar, that is the nulling fraction, the amount of time it disappears, and the null length, the length of time for which pulsar is not visible. There is not much data on the null length. I understand many people, including Professor Deshpande, who's part of this workshop, is working on that. So these are the two markers which characterize the nulling pulsar. And last time we have discussed that there are various kinds of nulling pulsars. The classical nullers, only a few pulses disappear every now and then. Intermediate nullers, very, very long pulses. Intermediate pulsars, they're mostly nulling. They come up only now and then. And then RADs, which people for a long time thought are probably extreme cases of nulls, but we are sort of slowly coming to the conclusion that probably they are not associated with nulling pulsars at all. And this is what we saw last time, that this is in the magnetic field spin period diagram, and here are all these gray dots are your radio pulsars, and these red ones are the nulling pulsars, and you see that they are very close to the death lines on the right hand side. Now, let us then come to the glitches of the radio pulsars. As I have said, that this is a picture of the glitches of Vela pulsar, in which glitches were observed for the first time. Now, last time I have mentioned Crab pulsar, which is very, very important from all aspects of neutron stars. People are continuously monitoring Crab pulsar to see what is happening there. Now, Vela is another such pulsars, and both Crab and Vela are copious glitches, which means that they have glitches all the time. Also, interestingly, the nature of the glitches in Crab and in Vela are different. So, why the nature is different, I'll tell you in a minute. Okay, we have the numbers here. So the typical Vela glitch, a glitch is defined by the ratio of the change in the rotational frequency. As you can see, this is written by delta omega by omega, where for a typical Vela glitch, this ratio is about 10 to the power minus 6. So 1 part in a million, that is the change in the spin frequency for Vela. Whereas for the crab, the number is much smaller. It's 1 part in 10 to the power 9. So the crab glitches are much smaller compared to the Vela glitches. And you will see in a minute that they probably are two different beasts. So this is the first time between February and March 1968. Now I want to remind you that we had seen the first pulsar. That was discovered in 1967. So within 2 years, we are seeing this very interesting phenomenon called glitch, a sudden increase in the spin frequency. And in the same year, crab pulsar is also seen to glitch, though the numbers are much smaller. So suddenly, after the discovery of the radio pulsars, which are extremely stable, as I have said, that P dot is very, very small, and therefore they have extremely stable spin period, we see that there is this interesting phenomenon. Suddenly the spin period increases, and that's what we call a glitch. And so, shorn of all the details, this is what it looks like. So there is a secular spin down, as we know that the pulsar is slowing down because of the radiation, and so the frequency is increasing. I'm sorry, it's decreasing. And then there is a sudden jump, and then it slows down again. And in many cases, it actually retraces the path which it would have followed had there been no interruption or had there been no glitch in between. So it's called a recovery, but that may or may not happen in all the pulsars that are showing glitch. So if you look at the same picture in terms of the spin period is increasing with time, and then suddenly it decreases, and then it starts increasing again. So this sudden decrease may or may not be followed by a relaxation towards the unperturbed P, the P that it would have obtained had there been no glitch. So this is the characteristic, the main feature of a timing glitch. Now, there have been about 200 pulsars, radio pulsars, in which glitch has been observed. Now see the interesting number here, there are also about 200 objects in which we know of nulling. Now, you must remember that these numbers are not sacred. Why they are not sacred? You can find that nulling, it's very easy to understand. You see that every pulsar is not being monitored all the time, like Vela and crab. Now, Vela and crab, everybody is looking at it all the time. But that is not true of all these pulsars. Now, we had about 3,000 pulsars. If you go to the ATNF catalog, which I said you must go and play with. So now we are not monitoring all those 3,000 objects all the time. So if some of the pulsars are sleeping, so to speak, nulling some of the time, we probably do not know. Probably there are huge number of objects which are nulling. We do not know, because if we observe them today when they are active, and then we observe them 5 years later when again they are active, we do not know if they had nulled in between. Okay, so we only know of about 200 objects which are nulling. Now, glitch is a slightly different kind of beast, because if there is a glitch between today and 5 years later, when somebody else decides to observe the same pulsar again, if there is more or less perfect recovery, as I said, there could be a recovery, the pulsar could go back to more or less to the original value, original in the sense of it was flowing down and it would have followed a path, and had there been no glitch, it would have reached certain value of the spin period. Now, if the pulsar comes back to more or less that value of spin period with some small mismatch, which can be attributed to timing noise, some random change in the pulse period, then we may not know that this object has had glitch episodes in between. So therefore, these numbers, and sometimes we have observed and discovered a pulsar and it did not show anything very exciting at the time of discovery, and then people forget about it. Oh, it's there, we have discovered it, and nobody thought of going back to it again. So there are many such pulsars. So we really do not know if many more of them are glitching. So therefore, this 200, about 200 objects which are nulling, about 200 objects which are glitching, is probably a very small subset of objects which are doing that. We do not know about them. Nevertheless, so there are now, as you know, that the crab and the vela are showing glitch episodes again and again continuously. So a particular pulsar may have many glitches that we have observed. So far, there are about 600, close to 600 such glitch episodes that we have observed in about 200 objects. And what we can do, the first thing we should do, and people who have done, undertaken the projects with me last time, they know that the first thing we do is do a statistics. We have a bunch of numbers, and the first thing we try to do is fit a histogram to it. Okay, and try to see what's the nature of the data. And the nature of the glitch data, this is a beautiful thing which I saw for the first time in 2013. And I see one of your instructors is Sandeep Kataria, and he came to NCRA to work as a summer student, and he played with the glitch data, and that's the first time I saw that this data has this beautiful bimodal nature. You see that there's a plot which is taken from somebody else's paper around the same time, 2013. And you see that it has a very clear, beautiful bimodal nature. So obviously the large glitches and the smaller glitches are definitely coming from two separate populations, indicating probably there are two different processes which are giving rise to them. Now, there are many theories afoot why they are different, and we, meaning me and some of my collaborators, we also have certain ideas about possibly what might be going on, so that we have two different this kind of bimodal distribution. But one thing is very clear and everybody agrees upon is this bimodal distribution must be indicative of two different phenomena. And you can clearly see that the vela glitches which are here and the crab glitches which are there, they belong to two different populations. So vela and crab are probably going through different processes which are showing up as a glitch in their periods. So now, before we get into the physics of the glitches, let me also try to show you something very interesting. Now, this is again a spin period magnetic field diagram of the radio pulsars. The red circles are the objects which are nulling, and the blue stars are the ones which are glitching. And you see that overall, there are two things that I want to make a note of, is that you see the red ones are on the sort of on the average below the blue ones, which means that if you take a particular spin period, let us say we take a spin period on the log scale, this is 0, so this is 1 second. So at 1 second period, you have a number of objects which are nulling, and you have a number of objects which are glitching. So you see on the average, on the average, the nulling pulsars have lower magnetic field compared to the glitching pulsars. So glitching pulsars seem to have a higher magnetic field compared to the nulling pulsars when they have very similar periods. Also, there is this region in which there is an overlap. In this region, you have both the nulling pulsars and the glitching pulsars. For example, you see this region, there are mostly nulling pulsars, not glitching pulsars. And in this region, clearly no nulling pulsars, but only glitching pulsars. But in contrast, this is the region in which you have both the nulling and the glitching pulsars. And please go back, look at the catalogs that I have mentioned. You will see that there are quite a few objects which are showing both nulling and glitching. Now, that is one interesting aspect I want you to take back from this lecture, if nothing else, is that there are objects in which you see both nulling and glitching. So now we have talked about the glitches. And now let us try to understand why such a thing happens, because I say that this is very unusual. So nulling is a process which we do not understand, but we may try to understand it as something that is making the emission process stop. Now, what that is, we are not yet very certain about, but something is happening which is making the emission process stop. Whereas in glitch, we seem to have a problem from our high school physics understanding. Okay, so even without going into details, there is an isolated object in the sky, and then it suddenly gets an extra bit of angular momentum. And where does that angular momentum come from? It's an isolated object floating in the sky. So that is what we have to understand. And therefore, we have to go inside a neutron star. Most of you know, people who are listening to neutron star talks and doing something with a neutron star, that the mass is from about 1 to 2 solar mass, radius is about 10 to the power 15 kilometer. So it has a very high density, equal to nuclear density, and therefore it can sustain very fast rotation. And the minimum spin period possible for a neutron star is about half a millisecond. And please go to the ATNF catalog and see for yourself what is the minimum spin period of a neutron star that we know. And you will see that it's not very much larger than half a millisecond. All right. It also has a consequence of being able to sustain a very, very strong magnetic field. So interior magnetic field, the maximum value of the interior magnetic field for a neutron star could be as large as 10 to the power 18 Gauss. People who are familiar with the Tesla, that's 10 to the power 15 Tesla. Now, of course, that magnetic field would not be visible at the surface. Surface magnetic field values would be around 10 to the power 15 Gauss, and that's what we have seen so far. So again, go back to ATNF catalog and see what is the maximum value of the magnetic field you see there. So this extremely fast rotation and very strong magnetic field has their own consequences. So then the first question that we need to answer is, what is the what is giving us this very strong magnetic field? So we know that if there is a magnetic field, there has to be currents which is sustaining that magnetic field, and so therefore we must go and see what is there that gives rise to this extremely strong magnetic field. So now in the interior, as I have said, the average density is like a nuclear density, and the material, because of the extremely high density, this material is degenerate. Now, please go back to your statistical mechanics books and remind yourselves that if the density is very high, the Fermi temperature of a system increases, and therefore it becomes more and more probable for the system to be in a degenerate state. And that is what happens in the case of neutron stars. The electrons, the composition of a neutron star is such that it's because it is about 90% neutrons. That is the reason we call it a neutron star, though it's not 100% neutrons. So there are about 10% protons and has to be same number of electrons to keep it charged neutral. So the electrons inside a neutron star, they are degenerate, but they're relativistic. Whereas the protons and neutrons both are degenerate, but they are non-relativistic. I would urge young people who have not done these calculations to go do these back of the envelope calculations and sort of convince yourselves that all the particles, the electrons, protons, and neutrons are degenerate at neutron star densities, but whereas electron is relativistic, protons and neutrons are not relativistic. So this is a high density, zero temperature system in the in the language of statistical mechanics. It's a zero temperature system. The real physical temperature could be as high as 10 to the power 6 Kelvin for isolated neutron stars, isolated old neutron stars, but it's an effective zero temperature system, and therefore it has various interesting properties. So the crust is like a metal. The metal we see all around us. The outer crust is degenerate electrons plus neutron rich nuclei, not like the material that we see on Earth, but weird isotopes of such materials, known elements, which have many, many more neutrons. In the inner crust of neutron stars, we have degenerate electrons, again, neutron-rich nuclei, but we also have a bit of free neutrons floating around in the interstitial spaces of a crystal lattice. You know, a metal is basically the internal structure of a metal is like a crystal. And so in the interstitial spaces of an ordinary metal, we only have electron gas. Here we have the neutrons, a neutron gas, but these neutrons are superfluid, and that is very important for our purpose, for today's purpose. Okay, they are very important in the context of glitch, these superfluid neutrons. Now, in the core of the neutron stars, we have degenerate electrons, superfluid neutrons, and superconducting protons. Now, superconducting protons, again, are very important from the context of the magnetic field. And deep in the interior core, there may be exotic phases of matter, which we would not go into. But the important points to note here, the rotation of the neutron star, if the neutron star, which has a mass, similar to a solar mass, or maybe twice that of the solar mass, and is rotating so fast. As I said, the minimum spin period is about 1 millisecond. So it is a huge amount of angular momentum. You must go and do these back of the envelope calculations. And this angular momentum is supported by vortices in neutron superfluid. Now, you must go back to your statistical mechanics books and sort of revise your understanding of superfluids. And so a superfluid cannot rotate like a solid, rigid, solid object, even though from outside a neutron star for us appears to be like a solid object, but it is harboring superfluids inside, and therefore the rotation must be supported by vortices in the neutron superfluid, because neutron is the bulk of the material, and that is in a superfluid state, and therefore the rotation has to be supported by generation of vortices in the neutron superfluid. Similarly, the magnetic field, because the protons in the interior are superconducting, magnetic field must be supported by superconducting fluxoids. And there is a possibility of having the magnetic field supported by currents in the crust, like you can have currents in a metal, and which gives rise to a magnetic field. In a neutron star, you can have crustal currents, but there is a high probability of having superconducting fluxoids in the interior. And slowly we are converging on the idea that the magnetic field of the neutron star is a combination of both crustal currents and superconducting fluxoids. So this is a sort of basic basic picture of the neutron star interior, the way we understand it today. So this is the outer crust and the inner crust and the outer core. And you please note that in the inner crust we have superfluidity of the neutrons, and in the outer core we have superfluidity of the protons and the neutrons. And this inner core may be large, may be very small, may be non-existent. There is a lot of debate about that. So it is quite possible that the entire core is made up of superfluid neutrons and superconducting protons, and there is no exotic component there. We do not know, but for our purpose, we would assume that the entire interior is superfluid protons and superconducting protons and superfluid neutrons. Now, there is also this bit near the core crust boundary of a neutron star. So the crustal lattice is slowly going into the core region where there are no nuclides. There are only neutrons and protons, and so the nuclide kind of dissolved. But before the nuclide dissolve, it goes into something called a pasta phase. As you can see that they look like, you know, elongated rods and flat shapes and so on. So this is the inner region, the deep interior region of the crust. And we are coming to understand slowly that this region plays a very important role in much of neutron star physics, in particular the physics that is related to the superfluidity of the components. So very, very complex and very difficult kind of physics which experts are looking into. In particular, Shamil is an expert, is a young expert in this region and is doing excellent work. But this is something exciting, interesting, but and a lot of work is being done, but very difficult. Okay. So therefore, as I said, because of the extremely high temperature, extremely high density, these systems are degenerate because the Fermi temperature is, as you can see, extremely large. And the real physical temperature, please ignore this D here, it's a typo. So real physical temperature of an isolated old neutron star is about 10 to the power 6 Kelvin, which is, as you can see, is much, much smaller than the Fermi temperature. So the system is in effective zero temperature state. And because of this, there is BCS-like pairing of neutrons and protons, which give rise to the superfluid behavior. The superfluid transition temperature itself is so much larger than the real physical temperature. So even though the system has real physical temperature, we can completely ignore that, because that physical temperature is much, much lower than all the relevant important temperatures of the system. So we can completely ignore that temperature and deal with neutron stars when we are talking about the interior of the neutron star, not at the surface physics. But if we are talking about the interior physics of the neutron star, we have this advantage of taking it as a zero temperature system. Now, that is usually not true of other astrophysical situations, but here we have this advantage. Now, yeah, what it says that various temperatures that we are talking about, critical temperatures of various superfluids. So what you see that in the interior, in the core, there is a particular kind of neutron superfluidity, a particular kind of pairing. And protons, of course, have a kind of pairing and a superfluidity. Their superfluidity basically depends on if you have fermion superfluidity. Protons and neutrons are fermions, please remember. The standard kind of superfluidity one studies in regular statistical mechanics courses is the helium-4 superfluidity. And the helium-4 is a boson. So it comes from the bosonic properties of helium-4. That kind of superfluidity comes from the the bosonic properties. Now, when one talks about superconductivity in the terrestrial situation, one talks about electron superconductivity, of course. Now, electron is a fermion. So what happens is, when one talks about such superconductivity is actually superfluidity of charged particles. So because the interactions, there are other interactions, difference in interactions, the physics is not exactly the same, but in layman's terms, zeroth order superconductivity is nothing but superfluidity of charged particles. Now, electrons are fermions. So when we say superfluidity of electrons, we talk about pairing, effective pairing of electrons. Now, if you have pairing of electrons, so what you have are effective bosons. So if you have an even number of fermions effectively pairing, you have a boson, and then you run the standard argument for superfluidity. Of course, the interactions are different. So a similar thing is happening here. For protons, we are calling it superconductivity because protons are charged. Same kind of physics is happening for neutrons. We call it superfluid instead of superconductor because they are not charged. It's just a nomenclature. Now, the pairing is different for neutrons here in this region and in this region of, because the densities are different. So therefore, the interactions and etc. are different. But you see that, so we have neutron superfluidity here, we have neutron superfluidity here, and we have proton superfluidity there. But in the outer crust, there is no superfluidity. Okay, so we have superfluids, neutron superfluid in the entire interior of the neutron star, except for a small region of the outer crust, where the total amount of mass contained in that outer crust is less than about 1% of the neutron star mass. So therefore, the almost the entirety of the neutron content of a neutron star is in a superfluid state, and there the rotation is being supported by rotational vortices. So this every rotational vortex has a quantum of circulation, it's quantum of angular momentum. Okay, and that quantum of angular momentum is very, very tiny. So 2 into 10 to the minus 3 in CGS units. So for a neutron star of having a mass of about 1.4 solar mass, which is the canonical neutron star mass we love to use, and a spin period of let us say 1 second, the number of such vortices is about 10 to the power 16. So you have that many vortices threading the entire star and giving it its rotational angular momentum. We'll ignore this for the moment. However, all these vortices, so in the interior, what happens is you have neutron superfluid and you have proton superconductor. So there are neutron vortices and there are magnetic flux tubes, and they are intertwined because neutrons and protons are would be interacting via strong force. So these things are tangled, and therefore the physics is very difficult. On the other hand, in the crustal region, in the crustal region, where happens is there are neutron vortices in the neutron superfluid, and there are nuclei in the lattice. Now, what happens? These neutrons would interact with the nuclei in the lattice. So, what happens is the neutron vortices, the rotational vortices, they are interacting with the lattice points of the crustal region. And what is happening is, we call sort of in technical terms, we call these vortices are pinned to the lattice sides. There is strong, there is interaction between the lattice points and the neutron vortices, neutron superfluid vortices, and we call that they are pinned. So therefore, what is happening is, when a neutron star is slowing down, you remember how is the angular momentum of a neutron star is obtained? By having a certain number of rotational vortices, as we have discussed, seen in the earlier slide. So if it has to slow down, it's not a rigid body, it cannot continuously slow down, it has to get rid of certain amount of rotational vortices. That is, throw some of the rotational vortices out. Now, these rotational vortices are pinned to the lattice sides, so they cannot be easily gotten rid of. So what happens is, as the star slows down, the solid crustal region of the star is slowing down, but the superfluid cannot slow down because it's pinned, and it is not being able to throw out those vortices. You can imagine them as like threads tied to points, the lattice points. So what happens is, when the slowdown, when the difference between the angular momentum of the solid crustal region and the superfluid reaches a certain value, so that the force on them, because of the differential rotation, is so much that it is able to unpin these vortices from the lattice point, then suddenly a number of the superfluid vortices are thrown out. Now, superfluid vortices thrown out means you have this extra angular momentum suddenly thrown out from the superfluid component of the star. So the superfluid component of the star has suddenly gotten rid of some extra angular momentum. Where does it go? It goes to the solid crustal region of the star. Now the crust suddenly gets some extra angular momentum. Extra angular momentum, what happens? It spins up. So that is at the basis of the glitch phenomenon of neutron stars, getting some extra angular momentum, not from an external torque, but because in the interior of the neutron star, there is the superfluid component, which is tied to the lattice points and which cannot continuously unpin. Okay. So now you would feel that this is very good. So we have understood, and now there should be no problem. But there is big problem. If we theoretically calculate what should be the difference between the rotation rates between the superfluid component and the crustal region, so that there is enough force to unpin these lattices, we should be able to calculate. We should now that then every time there is such a build-up, there should be an unpinning of the rotational vortices, and there should be a glitch. So in other words, the glitches should come in a periodic fashion. We should be able to predict them. Unfortunately, we do not. We cannot. We haven't been able to predict glitches. Only in some very special pulsars, in which glitches come in a very regular fashion. and we have been able to sort of predict the occurrence of such glitches. But in most cases, that doesn't happen. And one of the reasons why that doesn't happen is what this is my understanding is that you have seen that the crab kind of glitches and the villa kind of glitches, they seem to have two very different sort of two separate Gaussian kind of distribution. When we when I showed you the histogram for the glitch magnitudes. Now, if both of these processes, and we said that they are probably coming from two different processes. Now, if both of these processes are happening inside a given neutron star, then you are getting glitches coming from two different mechanisms, and you have no way of distinguishing which glitch is coming because of which mechanism, and therefore your prediction would also it will be very difficult to predict that. Because you remember that a Gaussian is not a sort of, you do not say that okay, this particular value of the glitch is large, so therefore I attribute this to this mechanism, and the value of this glitch is small, so therefore I attribute to this mechanism. That is not entirely correct, because we know that the Gaussians have sort of infinite tails, and so therefore one particular large glitch may have come from the other mechanism, and one particular small glitch may have come from this mechanism. So it's not very easy to separate the glitches. We can only do so in an average sense, not for a particular glitch. So therefore, I think this is one of the reasons why it has been difficult to have a theory which has been able to predict glitches very clearly, correctly. Okay. So summary of what we have discussed so far. So the superfluid dynamics in the crust. The superfluid spins down, number of rotational vortices must go down, but vortices are pinned to the inner crust. When the the rotational frequency of the superfluid and the neutron star as a whole becomes very large, there is unpinning. This unpinning gives rise to results in the transfer of angular momentum, and that shows up as a spinner. Now, you will ask me, this is only one mechanism you have been talking about, and you keep saying that there is probably two different mechanisms. So where is this other mechanism? The other mechanism that has been suggested by people is that it's like a crust quake. We all know about earthquakes and the mechanism which gives rise to this earthquake. So it's a very similar mechanism of crust quake. So the neutron star is continuously spinning down. So therefore, there is a centrifugal force on the crustal region, and the ellipticity should change. There is one particular ellipticity which corresponds to a particular value of spin period. When your spin changes, and because it's a solid, it hasn't automatically adjusted its ellipticity, so there will be mechanical stresses that would be generated, and that would give rise to the cracking of the crust. And cracking of the crust means the moment of inertia changes. Here, this change of moment of inertia results in a change of the spin period, and that may give rise to crust quake. Now, there are possibilities of the crustal energy not being sufficient for very large glitches that we have seen, and probably the core region of the interior region of the neutron star, the superfluids there, is also important. Probably the magnetic field has something to do with the superfluid dynamics, because they are entangled in the core, as I have told you. So all these theories are being tested now, and a lot of work is being done. We seriously do not understand a lot about the glitch dynamics yet. Something interesting that is happening is one of the very exciting suggestions that came from Andrew Line in 2004, and one of their observations indicated that a pulsar which is glitching frequently probably is showing that the secular magnetic field is increasing. So now it's very difficult to find a suitable model which makes the magnetic field increase inside a neutron star. I mean, people are not even clear about how a magnetic field is generated inside a neutron star, let alone how you would be able to increase the magnetic field. So, but there are theories, and people have some idea as to how this can happen. So there is a suggestion, would the pulsars which are glitching very frequently would increase their magnetic field so much that they would show up as magnetars? We do not know. This was an interesting suggestion. Unfortunately, hasn't been hasn't been shown to be a successful theory yet. So the summary of glitch phenomenology is it's basically, as you understand it, it's probably coming from catastrophic vortex unpinning, thermal pulse due to starquake, crust cracking due to magnetic stresses, likely two different origins for glitches. We must understand the relation between glitch and flux expulsion. As I said, the glitches do not come with some regularity. Do multiple glitches really transform a radio pulsar to a magnetar? One doesn't know. So this is where I would like to sort of end my presentation for today. And what I have been worried about is that on the face of it, the null and the glitch seem to be very, very different kind of phenomenon. And so far, some of our understanding suggests that whereas the nulling happens in pulsars which are somewhat old, and the glitching happens in predominantly young and higher magnetic field pulsars, there still is this question of objects which are showing both null and glitch at the same time, and also the fact that the objects for which we know to be nulling or glitching is a very small subset of the number of radio pulsars that we know of. So once we have many more objects observed to have null and glitch, would you be able to find a connection between them? Because there are these objects which are going through nulls and glitch at the same time. I mean, the same objects which have episodes of null and have episodes of glitch. Are these two phenomena connected somehow? Now, this is one question which has been bothering me for a time, and I am hoping that some young people would also be intrigued by this question and would want to look at this. Thank you very much.
Thanks so much, Sushan. I already see some questions on the chat window. I think you can see them too.
Yeah,
or I can read them out for you.
Take a look at that.
So yeah. So the first one is there a way we can observationally understand the inner layers and working of pulsars? Would astroseismology help? If so, have we to some extent tested observationally this theory of unpinning of superfluidic neutron vortices to result in a glitch?
Okay. Very difficult question, which hasn't been answered. No, we really do not have any way of observationally understanding or seeing the inner layers of a neutron star. So all our understanding has to come from from indirect evidences. Now, as you know, in astrophysical situations, it's so very different from laboratory physics, because we can't demand something. We get what we get, and we have to understand the system from whatever signal we are getting. And so glitch has been one of the phenomenon which has given us a glimpse of the interior of the neutron star, cooling being another. Many of our cooling models have shown that the way the neutron stars cool, there has to be superfluid components inside. So that is how we understand what is inside, and from the extrapolation of known physics, we really do not have any handle of observational handle on seeing the interior of neutron stars. Okay.
That would be really. So you can. The next one is, can you please illustrate zero temperature systems, wet neutron star? And the other one is, what happens to unpinned vortices?
What happens to unpinned vortices? See, unpinned vortices, these vortices are not physical structures. These are quantum mechanical our way of understanding how a superfluid rotates. So this is a quantum of angular momentum. So the moment it unpins, that means you have got this extra angular momentum transferred from the superfluid component to the normal component. And that's what it happens. So you unpin the vortices, you get some extra angular momentum to the crustal region, which is non-superfluid. That's all it happens. So it's a quantum mechanical construct. It's not a physical thing.
And his first one, can you please illustrate zero temperature systems, wet neutron star? I'm not too sure whether that I understand what that means.
Maybe.
So SK, you can unmute yourself if you want. Okay. With neutron stars, maybe.
With neutron stars.
Maybe with?
I mean, that's what I have said, that neutron stars are effective zero temperature systems, because all the important temperatures are much higher than their physical temperatures. So that's why.
Okay, so thank you for a nice lecture. Is there any apparent correlation between nulling glitching pulsar population and their age estimated?
Okay, so young people, you have to go to ATNF and make the histograms yourself. I can show you. I have them generated, but I would urge you to go and do this, and you will see some interesting results there. It's very easy to do. Just go to ATNF, download the age estimates, and plot it.
Okay. There's another one. From pulsar kicks using study of proper motion and parallax, their distribution. Okay, that's for the age probably. So the second question is, how subpulses seem to behave when glitching?
No, there hasn't been any clear indication of any particular difference in behavior of subpulses when a pulsar is glitching. But I have not seen it in the literature, but now that you have asked this question, I would I think that is something one should go and check. I haven't seen it particularly mentioned in the literature, no.
Mm-hmm. Mm-hmm. Okay. So are there any other questions? And Sushan will obviously send me the stuff which I will put for the projects, proposed projects.
Yeah.
And that. So Sushan, that was a really very nice lecture, very nice one. And
thank you very much.
the good part is the response in terms of the questions, right? Though the number is small, but the questions are many. So that's what makes it fun.
Yes.
Yeah. So please, does anybody else have any question? If you want, you can even unmute yourself and ask, or go ahead with the chat window. Either of the two, whatever you want. Okay. Fine. So I don't see any other questions. So Sushan, thanks so much for a lovely lecture. That was really very nice.
Welcome.
And please, everybody, hold on. This is going to be a very good Sunday. So don't. Yeah. Thanks, Sushan. That was really
very everybody,
nice.
And thank you, Priya, very much.
Oh, no, this is real fun. And actually, you know, see, in this case, people are actually seeing proper research problems and, you know, thinking. And that's where, you know, the whole creativity of science shows up, right? Where people are actually thinking and, you know, building up. So that's really nice. And thanks so much, Sushan.
I must say that thank you very much to you and Nadam for creating this opportunity for you know, the young people to do this, and for connecting us to these young people spread out over the all over the place. So thank you very much.
Yeah.
Thanks.
And we thank you for your support.
And thank you all the participants.
Yeah.
Yeah.
And your support is very important for us. Students have really benefited from your lectures.
Yes.
Thanks a lot.
Yeah. Yeah. So thanks again.
Thank you.
There's so
Goodbye
many
for
thank
today.
yous. This is really Indian style thank yous, right? Okay. So please, everybody, hold on. Have your chai. And 12 o'clock is the second lecture by Patrick Das Gupta on cosmology. So we have Patrick's now doing cosmology at 12. So please, everybody join us.